Hi, Jason. Hi, everybody. How are you doing? Oh, yeah, I know. I hear about the physics test. Half of my class showed up last night because it conflicted the time. So I know just right now, I think a lot of the classes are getting ready for midterm. So I understand. I remember the physics days. I took physics for at UCR. It was actually pretty fun. I liked it. Um, but I'm glad those physics days are over. Yeah, at UCR they make us do like discussion with the TA. It's kind of like you have to go in and do the lab and then you have to meet with the TA to take quizzes and tests and ask questions. Lecture halls are only for concept covering concepts with the professors, and I had one that like it's really hard to I couldn't understand him. He had a very heavy accent, but I made it through. So if you take it into college, it's actually a little bit easier and pays less fast. Okay, let me get my files open. Let's check out our Canvas materials, your notes, and your assignments. This week we're gonna do Fibonacci for LC-3. So it's gonna be a little bit longer program. Let me zoom in here for the notes and okay. So let's download your assignments in your lab. I mean, your assignments in your notes. And then if you want, you can check out the lab, but we'll talk about the lab on Thursday. I still have one more week to finish for your class for grading. I'll try to knock it out before Thursday. I need this. Do you have any questions before we start? You did okay with your lab last week? I haven't looked at if anybody turned in the extra credit for the month of the year, but I'll check it out to see. And then what I'll do is I'll post solutions maybe in a week or so for that. So that way you can check it out if you're curious. Okay, so it's 6 o'clock. We're gonna go ahead and get started. I think there are quite a few people are gonna join us. So I'll go into screen share. Let me know if you have any questions. Minimize everybody here. Okay, so we are now in week 6. I'll post the recording after the session, depending on when Zoom gives it to me. And then we'll do the lab. We are gonna do a sequence, which is Fibonacci, and I'll explain that on Thursday. So we're gonna program in LC-3 But today we are going to work on looking at the notes. I posted the presentations, and which I took some of that and put it in your notes. But if you're curious about the PowerPoint, you can also see that there. The notes are located right above that. And then for your assignments, we're going to address some of the questions right now. So let's take a look at the notes. So this week we're going to talk about problem solving and dive a little deeper into looking at how we would solve the problem in LC3. We talked about instructions last time. And so by this point, I think most of you are pretty comfortable with using LC3 instructions, looking at, how to add, move things around. I think we still need to work on branching a little better. So we'll have some practice this week and then going into the next few weeks. I plan to release your project maybe. Originally I was going to release it week 7, but I think I'm going to wait till after spring break. So just give you a little break of, from school, and so you can relax and possibly have some fun. So when you come back, we'll talk about the project, and then that should give you ample time to kind of finish. Project is due at the end of the semester, but I will give you opportunity to work in teams. I will have a team sign up sheet, and we'll talk about the process when you come back from spring break. Okay, so spring break is scheduled to be mid-April. So you have a week off, and then when you come back, refresh. We will continue with additional labs, and so you will be comfortable doing your project. So today we're going to talk about solving problem in programming. And just to start, most of you have taken programming classes, but just, the overview is that when you write your computer programs, you want to incorporate a program that performs some kind of desired functions. And we use software to solve a lot of problems, right? From analytics to everything that you use. It could be for fun, but a lot of times when you interview for jobs, they ask you to solve a problem. So we have to take a look at what they're asking or what the problem is, and then be able to piece it into functions or tasks that we can address. So in 1960s, the structured programming really is a way that we can improve to address some of the problem. And we started with, in computing, we started with simply just creating systems and applications to solve arithmetic problems, calculation problems, and then eventually it became more complex as we changed the way we use the system. So now when you look at a problem, you need to think about how that can be broken down into sufficient smaller units. And that's important to see. I tried to put this, kind of introduce it in the last lab when we start looking at how to work with the algorithm, and when you pseudocode everything out, you really have to piece it out into the subtask. And it needs to be in manageable units. So that way, when you write the program, you really address some of the requirements. And in LC3, we would address it with subroutines, equivalent to what we see with functions in C++ or other languages. And so you need to really think about how you would systematically decompose the problem, right? From a larger perspective down to small pieces that can be implemented into your code. So that means that we have to break the larger tasks into the subtasks. And, from a processor standpoint, that is just going to be processes that will be incorporated from the start to the end of your program. So now when we look at the way that we solve the problem, you need to take the statement, right, like what you see in your LC3 lab. Based on the given statement, you need to convert the problem statement into algorithm. An algorithm is just procedures, step-by-step procedures on how you would be able to derive the solutions. And we want to refine that so that way we can convert the algorithm into what we normally use in LC3 machine instructions. So in the questions, it asks you, how can you use problem-solving techniques in assembly program? Describe the process of solving problem using programming. So what we would start with is derive the problem statement questions, and we will talk about the questions, right? Then we need to convert the problem statement into step-by-step description of subtasks. And this is when you start doing, when you build your pseudocode, you would then list the step and what you want to achieve in each of the steps. Then the next part is to correlate 3 basic constructs. And in programming, it's the same across all languages. Okay. We need to have a construct for sequential. Okay, things that needs to be in order, right? Like how the program would start. So looking back into last week lab, remember that we have input, and we would take that input, we would convert it from ASCII to hex by doing the subtraction. Once we have that, we would then store it, calculate it, then convert it back, then we have an output. So you need to think about the sequential process, and that would be the first construct. The second construct is to implement conditions, or what we call conditional construct. And this is when you see branching in LC3. Now, for other languages, we would see if else statement. Sometimes we need to incorporate looping, right? So control statement is part of the conditional constructs. And in all programs, we have to think about how we would implement conditions. Even in some cases where you want to use recursion, or you want to iterate through your program, okay? And that kind of brings us to the next part, which is iteration. And in our program this week, we would see that we want to implement loops, so that way we can iterate and generate the number in its sequence. Okay. So these are the 3 main areas that we normally address when we're trying to solve a problem in programming. So the element that we want to look at is the questions here. It says, how do we use LC3 instructions to encode the 3 basic constructs? So in sequential, we look at instructions that naturally flow from one to the next. There's no special instruction that needs to go from one sequence of the subtask to the next. Now, in some cases where we talked about jump, right, or unconditional branching, where if you want your program to flow to a specific area, you can do so by sending it to a different label, okay? And you would use label to identify that section of the code where your program should flow to. Now, when you implement conditions in where we want to branch positive, negative, and 0, or sometime combination of those, then you can send, right, you can control the flow by moving it to the label that would be tied to the specific condition when it's true. So if I'm checking for branching 0, right? The previous line, if the register stores 0, then it's going to move to the branch label that I'm giving it, that I'm putting in my code. Now for the iteration, we can implement iteration using branching as well, but iteration is often used with loops, so we can loop through. Maybe we want to put values in a set, a group, or a set of offset, right? A group of offsets, or we can generate some set of values to output. So here we would create code that converts the condition into negative, 0, and positive. And lastly, once we have the 3 basic constructs, we need to make a decision on whether there is any kind of adjustment. If the program would be finalized, then we would then document it. So the right approach is to really thoroughly think about how you would solve the problem, what components should be going into the problem solving process, and make a habit of creating pseudocode that would, so that way you can see how your program is flowed, or how you can control your program to be able to derive the solution. Many of my students write their program first and then they keep making adjustments. So the challenge in that is when you start writing your code first without planning it, is you might leave out something important, or you might not be able to see the big picture. And then when you go through, if you need to make changes, you might have to change your entire program. And that just take away the efficiency where you dedicate a lot of resource into writing a program that might not be effective to start with. Okay. So we wanted to take the problem statement, piece it out, look at the step-by-step, and break it into subtasks, implement the basic construct. And then once we feel that it would be the appropriate solution, then we would finalize the decision and document it. Okay, any question with 1? So even with last week lab, while we didn't have a Zoom live session, right? In the video, I walked through how we looked at the problem and then break it into different processes and subtasks, and then be able to address each of the tasks throughout our program. Okay, so we're going to do that again this week. Okay, so here it gives you the diagram on how to look at the construct sequential, conditional, and iterative. And so the example for this is the PowerPoint, the presentation, the people who created it, they used the example where you would obtain a character from the keyboard, then you would count and print the occurrences of the character in that file, examine the file, make sure it matched, and then print the number on the screen. So as you can see, obtaining the character from the keyboard is its own task. And then from there, it should flow to the next. So you have some sequence here. And then after the file is examined and it finds the match, then it's going to print. So when we look at this task and we put that into LC-3, that's pretty easy, right? When we start the program, we can think about how we use register 0 to obtain the input and then move it, right? So from basically this task, you have to kind of list out some of the things that you need to do in the code to make sure that we can obtain that character, store it, and then move it somewhere. Then next we have to find ways to count the characters. So then we would look at the subtask within that task. Okay. So here it shows you the conditional and iterative. Now iterative, you would have do the subtask over and over again. And we've seen this in the program where we would continue to ask the user to input X, Y, right? In the past, we've done a lab where it's infinitely loop. And as long as that condition is true. So that program never ends. Now, in some cases, you want the program to exit out at some point, okay? So here we see the example where it checks the element of the file, count the characters if that's a match. So in that, it's gonna check for the characters. If that's true, it's gonna check the next and count if match. If it's false, it's gonna exit out. So we can say that if it's false, we can halt, right? If it's true, it's going to come back. It's going to come back to the label, like how we use it in the last lab or the prior lab where we use a loop label and then we just come back to the loop. So it continues to send it there and then execute the instruction within that label section. Okay. And we will see more of this in this lab, and you saw some of this last time where we would use count and we can add the 1 to the count. So just like how you look at a for loop, right? You can increment, or if you're doing like a while loop, when you increment 1, basically you just use a register and you add 1 to it. So it counts up to 1. And as it do that, right? But in a for loop, we have a maximum, we have a ceiling on when it's going to stop. So you can have it check by doing branching, where it would branch, right? When it subtract, if it's positive or when it's 0, then it's going to move to the next section where it exit out of that for loop. Okay. So we can use count and we can do the increment with the count by just simply doing arithmetic operation there in order to have the condition that would be applied. Okay, so we can use control statement that way. Okay, so here is the section where I got some of the details and above it for page 1 and page 2. So when we look at the example, let's take a look at the example. So this example said to count the number of occurrences of the character in the file. The character in question is to be input from the keyboard. So that means that we have to prompt the user, right, enter a character. So if they enter a C, then we would take that C, okay, in LC3, we would have to convert it from ASCII to hex. Then we would want to be able to take that value and compare it in the file. So assuming that this file is at a location in memory, right, could be an array, then what we can do is we can take that value and we can compare it. And the way we compare it is to use subtraction. So if we subtract, then we can branch. So the first question that comes to mind is, where's the file located? So we have to do a declaration of the field. Where is the section of the memory where this information, this data is stored? Now, in a regular program, you might have a large or a small file, okay? And later on, we're gonna start working with stack and we're gonna look at memory array. So you would see that we would allocate a certain size of memory that will be dedicated for that type or that specific data. Okay, and then the next question, how should the final count be printed? And for LC3, we can simply do a put, but we have to store, right? If we loaded or if we store to start, then we load and then we put. Okay. And LC3 does not handle float, but we can use integers. So if the character is a letter, should I count both upper and lower case? And that's important to think about because when you're using upper and lower case in ASCII, that's different, right? Different values. Okay. So these are some of the things that you need to think about and how you would address these questions would be incorporated in the task. So for the second area, it tells you that you need to convert the statement to step-by-step description of the subtask. So we should start with what is the starting state of the system, right? How should your program start? How should your program end? What is the desired ending state? And then how do we move from one state to the other? Okay, what's the process in between? So for the 3 basic constructs, again, here it gives you some example. For sequential, do A, then do B. Conditional, if G, then do H. Iterative, for each X, do Y. And another iterative, do Z until W. Okay, so that kind of give you parallel example for the constructs. Now, we have touched on the construct, okay? And here it shows you how you can take a look at the diagram and really see how the subtask could be broken into, or a task can be broken into subtasks. A general instruction would be incorporating multiple subtasks. Now in LC3, we can handle this. Each of the tasks we can use with label. Okay, so if it tests true, then we can go to this label. If it tests false, we go to the other label and then we would do something there. And then once that's done, we can send it to the next subtask. And for iteration, we can have a test condition and go to subtask. Okay. Then if that's true, and then we can come back to the beginning again, like we said with the loop that we saw before. If it's false, then we can send it to the following subtask. Now we use the PC offset address, and that really is the address to the label fill, right? You can have a label and then you can fill it where you can point it directly to a location, or you can just simply have a label so you can control the flow of your program. Okay. So this is the example that they use. Okay. Now, when you do a start and a stop, so this is what I normally get from my students when they put, their flow chart together. And I always put comments in their pseudocode or their flow chart. What happened to your branches, right? What happened to this? How do you test your conditions? So there's expectation that when you put together your program, you have to think about the little details. I know that you do when you write your code, but you really have to plan that out before you write your code. So that way you're not missing anything. And some of my students, they put in comment for my project survey that sometimes for them, pseudocode is the hardest part, right? Because they have to keep making adjustment So if you plan everything out already in the pseudocode, you don't have to go back to your program and make adjustment over and over again, right? You can make changes to it and adapt changes, but at the same time, you can break it down into different areas and then you can build in the subroutine for that. Okay. Any questions with the example that's given? And then we'll take a look at it, how that would be on LC3. Let's talk about the next question. Okay. So the next question asks you, question number 2, it says, what should you do when your program does not work? Describe the debugging process. Okay. Check your syntax error. That's the first step, right? There might be typo. And then also check for logical error. Okay. So if you're not getting the proper output or the program is halting where it's not supposed to, then you need to check for logic error. And then if you just get wrong data or something that's abnormal, then you should check for data error. Now in LC3, you're able to do step over, right? You can put a breakpoint in certain areas so you can see. It's a little bit harder to visualize in LC3 where there are multiple instructions, which is a very simple thing to achieve. So it's important that you see every single piece that needs to go, either sequentially or conditionally, so that way you can really be able to debug your program. Okay, so and you don't have to comment every line. We've been commenting every line, so it helps you see what's happening at a certain stage, right? But if that helps you, you need to add the comment so that way you know what that part of your code is doing. So in the notes, it talks about debugging. And for LC3, the two areas that you need to really check, right, is your register and your memory. And you need to maybe put the breakpoint on certain instructions so that way you can see why it's not working like you expected. So the statement here, it says time spent on the problem statement can reduce the time spent on debugging. So if you plan out and you really clearly break down, you decompose the problem, that's going to help you in the debugging, right? That's going to reduce the time. So we want to examine the sequence of instructions that's being executed, how it's going from one instruction to the next, or how it moves to a different label. We want to keep track of the results that's being produced, because sometimes when you move things across registers and copy them, right, you have to track which register is storing which value, especially when we deal with multiple inputs. And for our project, we will. We need to compare result from each instruction to the expected results. Okay. So that's how you're able to trace your program. And in the first few weeks, right, in the last couple of weeks, I show you where you can test your value by setting your values and then be able to look at your register and your memory location, because sometimes you can't see it in register, but if we can set it into the fill location, we can clearly see what it's supposed to be, right, after that program is ran. So because sometimes we don't display values in console, right? We only are able to see that at the memory location or in certain register. Okay. How we store the values in memory and how the register hold the values. And we need to take a look at how the sequence of the program would be based on the instructions that we're using. Okay. So as you, if you step through or step over, you would start seeing how values are being changed in your simulator. So here it shows how you can set your breakpoint. Okay, and the buttons next to run, right? You can set your execution sequence. So these are for you to use. And then you can look at the memory addresses, right? The value that's giving you and the instruction as it goes, as your program will flow. So as we mentioned earlier, syntax is based on rules on how that program language is what it's allowing, right? Just like how we write in English compared to if we write it in Spanish or French, okay? And often it's just error in the typing. So we want to check syntax. For logical errors, we want to look at what could be wrong. Trace your program. And in even Python or C++, when my students have issues with logical error, you know, sometimes you can narrow down the section and check that section, but sometimes you have to look at line by line. Okay. Now, unlike the other languages, we're not going to be able to catch exceptions on this one, right? You can handle input validation and things like that, where you would use a label to be able to control the input. But other than that, unlike higher programming languages, you don't, you know, there's not exception handling. And there's no library that will handle that. So at the low level, we would do everything manually. Okay, and then for data, we need to make sure that we look at how input, and then we wanted to test with using inputs, and you can use the set value to test. Okay, we saw how that's done. Okay. So for 3, it asks you to define systematic decomposition. And all that is we decompose each subtask into smaller subtasks and even smaller subtasks than the second step until you get to the machine instruction level. Right? So like when we say we're going to take 2 plus 2, at the instruction level, we have to add 2 to a register, right? And then add two to another register and then add those register and put it on a third register. So we would have many subtasks that would represent your machine instruction level. Any question with 2 or 3 on the assignment? Okay, so we addressed some of the debugging area, but for question 4, how should a program be debugged? Describe the step in debugging. Examine the sequence of instructions that's being executed. Keep track of the results that's being produced. Compare the result from each instruction to the expected result. Okay, so we need to look at the flow of our program and instructions. We need to track the result that's being produced. We need to compare the result to the expected result. Okay, any questions with 3 or 4? So make sure that we know of the debugging process, the type of errors. Okay, you might see some questions like that on final quiz. And how to solve a problem. Okay, so let's go through and look at the type of error. So for 5, it asks you to determine the type of errors in programming based on the given issues. A, incorrect instruction type LOAD instead of LD. So that's syntax, right? Because in LC-3, it won't understand load LOAD compared to LB, which is a direct load. For B, if the output of the program used negative value for absolute value of x plus y is greater than 0, then you have a logical error. So for B, that will be a logical error. For C, if the data input is less than the given expected test value in the problem statement, that will be data error. Pretty simple and straightforward. Okay. Any question with 5 before we move on to 6? All right, so for 6, it asks you to write the problem statement questions, convert the problem statement into algorithm using stepwise refinement, and convert the algorithm into an LC3 program. Okay. So let's take a look at the criteria. And we've been seeing this all along, right? Since week 3, we have been looking at the problem statement. Okay, so for 6, it asks you to create an assembly program that contain the following criteria. X is set at location hex 3400. Y is set at location hex 3401. X is equal to 3. Y is equal to 2x. Display the value for Y. Okay. And if you don't use put, we have to store out Y to location. Okay, so what I did was I added the red so that way you would see. Okay. So what we need here is that we need to fill X at hex 3400 when we pseudocode that, right? And so when we use the label, that will be X dot fill hex 3400. And that just means that we declare label X. Then we would go to the next criteria. We would then fill Y at hex 3401. And we declare label Y. So in red is what you would see as equivalent, and that would be at the bottom of your program, of course. So for the next criteria, we would have to get X to be equal to 3, okay? Because we already filled for X, we need to load X label to register, right? And then we need to then add decimal 3 to register. So then we would have this. I did an LEIR1X, so we load label X to register 1. And you don't have to use register 1. We can start with register 0 if you like. Okay. And then we can add R1 with decimal 3. So that way we have R1 is decimal 3, which is equal to X. Then on the next one, we need to set Y is equal to 2 times X. So we first need to load Y label to register. Then we need to copy X register to Y register. And then we want to add for multiply. So multiplication just means what? It just means that we add repeatedly, right? So in this one, let me tap it in so you guys can see. So I first load the Y label to register 2. Now remember that Y is equal to 2X. So I first want to copy the X to the Y register so that at this point, R2 is X or decimal 3. Then I add itself again, so that way I would have 2X. So I would do an add R2, 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 because if I add itself, then that's going to be a multiple of that same value, right? Which is 6. Okay. So here I take a 3 plus a 3 and then put it back into register 2. So that will be 2X or decimal 6. Okay. But I'm not done, right? I need to store out. So I have to store Y label, or I'm sorry, store or register to Y label. Because that way I can go to the location and test the value. Now, because I store it to the Y label, okay, now if I don't store it, okay, that's why I put it in purple here. If you don't store it, you can simply take register 2, copy it to register 0, and then do a put. Let's do that instead of a load. Okay, so at this point, I'm going to comment this out because you can store and then test, but I don't think we need that yet. Okay, so the purple one, it's not required. So what we're doing is since we have register 2 as Y, okay, then what we need to do is we need to copy Y register to register 0 for display, because you remember when we use the put, we have to use register 0, right? So now after that, what we can do is we would then do a put. And so that way it would show, actually, I'm sorry, I'm missing something here. We need to convert. So if you wanted to do a put, you have to convert the value to ASCII. So here, because it's at register 0, right, we can do the subtraction like what we've done before to be able to do that, assuming that we would have an input for X. Now, if we don't do a put, okay, then we can store it out and we can check it that way. So there are two ways to address the display. It didn't tell you to display on console. It actually just said that display the value of Y. So if you want to display it in console, you have to ASCII convert it. If you just want to display it in the simulator at the memory location, which is an easier way for us, because in order to test Y, we have to have an X input. Okay? And we didn't do that at the beginning when we handle the X. We just simply add in the 3. Okay, so I'm not going to do the put for this one or the ASCII conversion. So I'm gonna scrap this. Okay, sorry about that. So what I'm gonna do is I'm gonna bring this down. So what I'm going to do is I'm going to store Y to register to Y location. Then after that, I'm going to go ahead and test by setting value. So no put. Okay. So after this point, what we can do is we can go in and we can set for Y and X, and then they run the program. So if you set for X, right? It says that X is at 3 and Y is 2 times X. If you run the program, then you can actually should check memory location. If you run the program, you should see a 6 at 3401. Okay. Any question? So this one's pretty easy. So here what we did was we, just put down the pseudocode, and then we convert that to instructions. So we broke it down to instruction or the subtask. So Eric asked, doesn't put require null for stop printing? That's if you're using string, and in this case, we're not using strings in our program. In the program that you did last week was when we used string, remember, and it needs null terminated character. So this one we didn't use dot strings, right? So we're fine. No. But we need to ASCII convert if you use put. So in the case where if you wanted to use put without having, because you already input the X here when you add it, you have to convert the value from hexadecimal to ASCII by changing the offset for it. And so, okay. You can still output Y, just you have to ASCII convert it. Anytime that you guys deal with console display, remember you have to ASCII convert. Otherwise, it's not going to work correctly. Okay, so I just got lazy and I didn't want to do that here, but you get the idea. We've done a lot of the programs with ASCII conversion already, so you should be all right. Sorry, my dogs keep wanting to go in and out. Okay, let's do the next one. Oh my God. I'm a dedicated door opener for my 2 dogs. All right, sorry. Okay, B. Create an assembly program that contains the following criteria. So we're going to practice some more. Okay. All right, this one's a little harder. Okay. So we have the criteria. X, Y, and Z are set at 3100 respectively. X minus Y plus Z is equal to 10. So we can say that Z is equal to 10 minus X plus Y. If X is 11, then Y is 4. So we can set it up that way. Z would be 10 minus 11 plus 4 is going to be equal to 3. Just for check. We want to solve for Z if X is greater than 10 and Y is less than 5. Check conditions for X above 10 and check condition for Y below 5. So why am I stating all of this? Well, number one, right? We can fill we have X dot fill and we would start at 3100, right? Y, we would do a dot fill at hex 3101, and Z, we would do a dot fill at hex 3102, because that's what it says respectively. So let me change this. Okay, so given the equation, we have 3 variables, X minus Y plus Z is equal to 10. But in the below bullet, it tells us that if you have, we want to solve for Z if X is greater than 10 and Y is less than 5. Okay. So with that, we would put down that let's assume, right? So if we move everything over, we would have Z is equal to 10 minus X plus Y. If X is 11, which is greater than 10, and Y is 4, which is less than 5, that's the criteria here, then Z is equal to 10 minus 11 plus 4, which is 3. And we can check it with these values. So to solve this, we would then check the condition for X is above 10. That means that we have to subtract 10 and check for positive. Okay. Then next we have to check the condition for Y. Y needs to be below 5. So we can subtract 5 and we want to check for negative and we can send it to the negative label. And then lastly, we have to display Z value. So what does that mean for us? We have to store value from register to Z label. And then we want to verify output at location, at fill location. Any questions? Okay, so what we did was we broke down the criteria into, right, instructions that we can use in LC3 program. And next we're going to write the program. Let me move this over to the next page. Okay, so let me double check this because I might have missed something when I did this before. Okay, so we filled on the bottom. Okay, that's the criteria that it tells us. We then would load X, Y, and Z. And so on this line right here, so I wanted, hold on one second, let me take this real quick. I want to put that here, so I'm going to double check. Okay, so we wanted to make Z is equal to 10 minus X plus Y. So what I'm doing at this line is I put 10 into register 3, which is this right here. And then since X is, and that would be Z, right? So right now I have Z is equal to 10. Then the next part I'm going to do is I'm going to set up the negative X and then add it with the Y. Okay. So right here is where I would have it subtract X for the next 2 line, which is the second piece. So when you look at the equation, just like what we talked about before, you have to piece that equation into chunks so that way you can process it in 1 or 2 instructions at a time. So after these 2 line, register 1 holds negative X. So I have it not because we load X to register 1. So here's the first complement. This is the 2's complement. So now at this point, I have R1 is negative X. And since I already load R2 with Y, then I can simply add all of them together. And I would have register 3 is equal to 10 minus X plus Y is equal to Z. Yeah, it's the same. It's the same as R2 subtract R1. Because R1 is negative X. I just wanted to keep it the same way that the equation is shown earlier, so that way it doesn't confuse you. So here's R3 and then R1 and then R2, and then we're going to put it back into R3 again. So R3, R1, R2. Okay. So now what we want is, now note that I did not branch yet, right? I simply set up the equation. Okay. But if you wanted to make sure that you branch for input validation, because the problem tells us that X has to be at a certain value and Y has to be a certain value. So you have to branch to check for input validation. in that case, meaning that, you know, it forces the condition to be above 10 and below 5. So here, what we can do after we have R3, right? R3 is going to be equal to this. Then we store that out to Z, which is what we need to display at the end of our program. Okay. Now, if I branch, okay, if I branch to check for X is greater than 10, where would I do that in this program? Anyone? So I have the core of the program written for you. Where would you add the branch? Because we still have to check for X has to be greater than 10 and Y has to be less than 5 as input. Prior to the add for R3 with 1. Why would you do that there? Okay, so Eric recommended that we should branch. So if you branch right above this add right here, what's going to happen is it's going to only look at what was loaded to register 1. Okay. The data validation before data processing. Makes sense. Everyone else agree or disagree? Because this could be the fate of your program, right? So if I do that here, right? If I do a branch, let's say, but I need to have some value in there for it to check. Isn't that true? Okay. So let's say that if I wanted X to be greater than 10 and Y is less than 5, how can I introduce that after I loaded it from the label? How can I make this right here? How can I get that happening over here? Subtract 10 if it's 0 or negative, start processing data. Okay. Valid point. Anyone else? Christian said, subtract 10 from register 1 if the result is positive, branch positive. Okay. And then what do you do in positive? Load or store? check to see why. Okay, so I'll do what you recommend and see how it's gonna go. Okay, so after we load the label, what we can do is we can subtract, right? So we can do an add R1 with a negative 10. Right, decimal 10. Okay. We can do a shortcut this way, or you can do a 2 complement. That's up to you. Well, let's do that. That's more proper. Not R1. Right? And then we would do an add R1 with a 1. sorry. I'm just blocking everything you could see. Okay. So here I put 10 onto register 1. Okay. And then I make it -10. So at this point, R1 is equal to -10. Then I can add a 10 again. Is that efficient? So if I do this, sorry, I forgot a comma here. And then you tell me to do a branch 0. BRZ go to then what's happening in my 0, right? Or if I wanted to do 11, let's see, if I do 11, check for positive, I'll do what you say. P pos. Surely. So now, right, I have a branch positive like you suggested. So what do I do in the positive? Store it out to Z, right? Can I have it like this? Okay, so question said, in the label positive, we can check for Y less than 5 and then branch again to subtract 5 from Y, but this time branch negative. Okay. So now, okay, so what I suggest is it's still gonna have to check for Y is less than 5. The dependent Y is not dependent on the condition of X. So what you recommended is what you have recommended is that would be Y is dependent on the X value, which is not, right? Because the equation stated that Z is equal to 10 minus X plus Y. So Y doesn't really depend on the input of X. Okay. So if you branch it to positive and you put the Y value there, it's gonna state that it's a condition of the branching from the X. Okay. So in the positive, what I would do is I would store it, because if we check for input there, if it's positive, then we would output the Z, and that was what we wanted to achieve here, right? And so we still have to force the Y is less than 5. After we load 5, we can do an add R2, let's say with the 4. Okay. And then we do a not R2, and then we would do an add R2 with the decimal 1. So at this point, R2 is equal to -4. Wait, do I need a -4? Oh yeah, I do, because I need to subtract it, right? And then we can then add R2, R2 with the 5, then we would do a branch negative, and we can go to neg. Now here, what do I do with the negative? I know what I can do. So in the positive, I'm going to do a store X. And then in the negative, I'm going to store the Y. Okay, I think I got it. You guys see what I did? Okay, so let's walk through it again, the complete program. Okay, so first, what we did was we validate the input for X. Okay, we load X, we add the 10 to register 1, which makes it here that R1 is 10, which is X, right? And then we not it, so here we would have it as negative X. Okay. And then we use a higher value to input for X because that would be 11, like what we had stated earlier. So 11 plus 10, this will be true. So it's going to push it into the positive. And when it goes to positive, I store X. Okay. Then, okay.
Professor,
Sure.
when we branch to positive, would it skip the rest of the lines after branch if positive?
No, so it's gonna go to the positive section. It's gonna do that. Then it hits a halt. Then it's gonna come back to what's next.
Okay, got it.
Yeah. So it's gonna. So basically, we force a conditional branch here. So it's gonna go to the positive section. It's gonna do its thing there, and then it's gonna come back and it's gonna continue at the next line.
Would it be the same thing for unconditional branch?
Yeah, I guess we can check for, we can do a PR or BR for the branch, but in that case, it would not check for positive in the case of the BR. So if I use BR here, it will just go to BR no matter what.
Got it.
Yeah, and we want to check for positive because we said that it has to be greater than 10, right? That's the if else statement that we use. If X is greater than 10, go to positive, store the value for X, then go back to load the Y, check for Y is less than 4, branch, right? And then come back to Z, load Z, and then store Z. Okay. So here, after it goes to the positive, store X, right? Because that's where our input would be, so we can see it. It wasn't required, but you wanted to see what that is. Otherwise, you don't have any tasks to complete in positive. Then you can do a Y is less than 5. We would load Y, add 4 to that. So at this point, R2 is equal to 4, which is Y. Then we not it. Let me think about this real quick. 4. Yeah, so it has to be less. Okay, so we knot it, so that means that here R2 is equal to -4. Then we subtract 5. Okay, so R2 is equal to 4 minus 5, which forces it to be negative. Then when it goes to the negative, it's going to store the y for us. Okay, so that will be -1. And let's see, -1, 11. So you have a +1, that will be 0. So your z should show as 10.
Professor,
Yeah,
if R2 is -4 and you're adding 5, it'll be +1. It won't be 4 minus 5.
oh yeah, I'm sorry. I meant to go the other way. That was what I was thinking earlier. Okay. So let's change this. I wanted to branch negative, right? Yeah. So now it should branch negative. Okay. Is that right? Can you check? So here I have 5, right? I knock the 5, now it's -5. I add the 4. Okay, so now it's branching negative. Sorry, I had it in reverse. Dyslexic. All right. Okay, so once it goes to the negative, then we would store the y. Okay, and so when it stores the y, you should see -1, right? And then when it stored the x, you should see a +1. So when you do the math in the equation, so you have a -1 plus a -1. So you have what, -1 here plus a -1, that's -2. So z should be 8. Okay, to validate that equation. Okay, so when it stores z should be 8. Because we hard coded in the value. That's what we did to make sure that we checked for the condition as it's negative or it's lower than 4 or higher than 10. So after it stores the y in the negative, then we would load the z, and then we would operate the equation here, right? And then so at this point, we finish out the equation there. And then that's it. So let me zoom. Hold on 1 second. I'm going to stop share. Let me zoom out so you can see the complete program. I know some of you are trying to edit it.
Can we possibly run the program too, just to check?
You can check, of course. That's what your simulator is for. Please check my code. You can run the program, you can test it, you know. And if you catch something, let me know, right? Because I do this stuff on the fly sometimes. I miss something, and if you can find it, that's great. You debug it. Okay, so it doesn't show. Let me share the screen again. I'm sorry, it's small. Okay. But so after the pause, I just have the neg, and then I store out. So I'll scroll down in a little bit so you can check. So this one, the way it's hard coded, you don't have to set value, okay? You can just jump to the location of the fill and see if it's actually putting in the -1, the -1, and then the 8. So you can check the equation, because the equation is that we have 10 minus negative, when we put the x in, right? That will be a 1. So -1. So that's a 9. Subtract another 1, that should be an 8. So yeah, Z should store out 8 as decimal. And if you have a better approach, because I think that this one can be cleaned up a little bit better with the way it's branching. But since I had it pretty much set up, I have to tweak it where it would be easy for you to see. Okay, any question? So a simple equation like that with two condition, right? With x is greater than 10 and y is less than 5, you see how many tasks that we have to put in this instruction. Quite a few in LC-3. So it's a lot easier if we break it down into pieces and then we start breaking it down into further subtasks.
Professor, for
Sure.
the last part, when we calculate the value for Z by adding R1 and R2,
Mm-hmm.
wouldn't the R1 and R2 values no longer be X and Y by that point? When
Yeah, it's actually just -1 and 1. Mm-hmm.
Okay.
Yeah, because we hard coded in, we put an arbitrary value here. So by R2, after this line right here, it's already a decimal 1 here.
Yeah.
And then on this, actually, it's a -1, I'm sorry. And then up here with the R1, that will be a 1. So we hard code it so that way we force Z to be a certain value to check the equation.
So yeah, so for that last four, we're technically not subtracting X and adding Y.
Right,
Okay.
right. But it's just the value in replacement of X and Y.
All right. Yeah. Okay.
Yeah. But if you don't hard code in the value, then you can do the set value button, which is the same thing, right? Like if eventually when you set the value, you just add that value to that register. So if you don't hard code it like this, then you just branch and then you just have to set the value before you run the program. Sure, you can do that. So I should say that it would be, this would be -1 and then plus a -1 there, which is equal to Z, which is 8. I love it that you guys are seeing this, right? And, you know, and of course you can come up with, you can solve this a little different and better, right? I'm just showing you how we can take a problem and be able to solve it. Okay. And then don't forget the .n. Otherwise, it's going to throw an error. Okay. Are we okay with this? Can we move on to the next one? Every time I come back, even though I wrote it, like, you know, the last time I taught this class, sometime I come back, I say, oh, I'm missing this and that. Sometime I, you know, so it's better if we just plan it out and then go back and fix it. Okay, so I think we can do the next one. Okay, for C, and I think that's it. So that should be all right. And if you miss something, we can come back to it. So let me zoom in a little more. Okay, so it asks you to write an assembly program that contains the criteria. A is set at 3330, B is set at 3331, and C is set at 3332. That's easy. We can do the fill for those. So I just fill them. And then it tells you that if A minus B is greater than 0, add 3 to R. Okay. So we have to fill R so that way we need, because we want a location to verify, right? And then we need to look at how we would branch for A minus B is greater than 0. So check for positive after subtraction. Now on the next one, it tells us if A minus B is less than 0, we want to subtract 2 from R. Okay. So branch for negative. Branch for A minus B is less than 0. Check for negative after subtraction. And then we need to subtract 2 from R. Then add 3 to R. And then if we branch for A minus B is 0, so check for 0 after subtraction. Then add 1 to R. And I don't think you need to have to set the value for R. Okay, so this is not required. I think you can set the value for A and B, and you should be all right. And you should see whether it's 3, 2, or 1, or I'm sorry, 3. Yeah, it'd be -2 if it's empty. But if you set in the value, you just have to add it. Kind of like what we did before with the P and the Q. Okay, so we have to fill all of these labels, right? And the R as well. So that those goes on the bottom for the declaration of data store. Then we need to load the register with the label. Then I had set up the negative B because it's A minus B. Then here I have A minus B. Then I have branch to positive, branch to negative, and branch to 0. And for the positive, I'll move this up so you can see it as a section. It's easier. Hold on. Get Word to cooperate here. Okay. So for the negative, I just simply add what under it's subtracting 2. Yeah, that's right. I subtract 2. Zero, 1, and 2. Oh yeah, I don't have any need for C. Sorry about that. So that's good. We can forget about C. Don't worry about C. Okay. So let's walk through the program. I load R to register 1. I load B to register 2. I load I'm sorry. I load A to register 1. I load B to register 2. I load R to register 3. I set up the first complement or the one's complement for B and the two's complement for B, so that way it becomes negative B in register 2. Okay, at that line. Then I do an add, and I have add R4, R2, R1, which R4 holds A minus B. And if you want to clear out register before you do all of this stuff, great, that's fine, right? Then I branch for positive. It's going to send, if it's positive when A minus B, then it's going to go to the positive section in which I add 3. Okay. I add 3 to I don't know why I use register 5 for that. Okay. I think I have an error there. Okay. Sorry, let me fix my register because that's going to be wrong. I don't think I need register 5. Okay. So now R3. Oh, this one is fine. To R. I forgot to store out. 2. Okay. So when we branch positive, then we would go to the positive section in which we would add 3 to R, and we need to store that out. Halt, right? If it's negative, when it checks, then it's going to go to the negative section. And in the negative, we simply put in, oops, R3 is going to be, it's going to subtract, the R is going to subtract 2. Okay. And we need to store that out to R. Okay. Then, okay, that's right. And then if it's 0, when it branches 0, then it's going to go to the 0 section. And in the 0 section, we're going to have it add, R is going to add the 1. And we're going to store that out. Okay. And then lastly, we just do the fill subsequently. And I don't think you need to fill C because we didn't really use C, but we use A, B, and R. Okay. Any questions? And then don't forget the .n at the end. So this one was like the lab 4 that we did with the P and Q. What happened to my chat on? There it is. For the negative R3 hex. So I add 2 to R3. I knot it, make it -2. R3 is equal to R minus 2. You can keep it. Okay, so I see what you're saying. I chose to use R5, right? Because so in the previous one, sorry, my comment is mismatched here. In the previous line, I have the first complement in R2, or I'm sorry, 2 in R3. So -2 is actually in R3, right? Then I take the -2 and I add it with R, okay? And then I put it into R5. So you can keep it as R3 if you want and then store it out from R3. It doesn't really matter. So more efficient is if you keep it in R3 instead of using R5. But I don't know, when I coded this previously, I probably had put it on R5 so I don't confuse myself when I track the register. But if you make it like this, you just have to store it from R3 so you can reuse the register. It would be the same. Because we have R originally loaded to register 3, and then we had add -2 to it. So by this point, right, R3 would have R minus 2, and I just put that onto register 5 so I could track it. Okay, any questions? Yeah, so Jason, you can use register 3. doesn't matter, right? More efficient is to use register 3. Keep using register 3 for the negative section, but if you, I just use another register. Okay. So on this one, we simply just check positive, negative, and 0, very much like the ones from lab 4. The one prior, right, we hard code in the value, but you can do similar to this and then be able to set the value. Okay, so don't forget all your fill in the dot n. Okay, so I hope these little mini exercises that we're doing instead of like the regular lab kind of help you in understanding a little bit on, you know, the arithmetic side, how to do the branching a little bit. Now, if you wanted to, let's say that if you wanted to use this and you wanted to make a function, like you wanted to do a subroutine with this, what you can do is you can build in a function for the subtraction part, right? Like a minus b, this part right here, okay? And then you can do a JSR at the beginning, okay? So if you do a subroutine, I'm gonna change the font so I can show you, okay? Let's do Pico Brown. You would have to do a JSR, let's say I call it sub for subtract, like this, right? And then we just do a subroutine call, okay? Then I would label this as sub, and then I just have to call it. So you have a function for the subtraction a minus b, and then in that you would then check. So does it really need it? Not necessarily, unless you wanted to keep repeating to subtract it so you can continue to call it every single time. But this allows us to do like a subroutine call. And so we simply use a label to handle that. And you saw this when we did the compare function. Excuse me. So if you want to implement a function, you can just do the subroutine call, right? And then below it, you can define it, okay? And then branch out and then use the label to handle the conditions. Okay, so we'll touch more on subroutine and JSR this week when we do the lab, and also the following week. Okay, any questions?
Oh, Professor, not regarding this lab, but do you mind or can you show the lab we just did recently, the part 2?
I will show the solution in a couple of weeks. I don't show it now because there's so people turning in work.
Oh, I see.
Yeah, and I think when I close out the extra credit is when I'm gonna post the solution.
Okay, no problem.
Yeah, I do it every semester, and some of my former students probably post it on GitHub too, if you guys are curious. But I have it on my GitHub. I will share the solution with you down the line. And there were many solutions that came in from last year. Some were better than other to handle the multiple input, like, you know, because if you start putting in like 10, right? And it's supposed to show the month. How do you handle the multiple input is really, it shows how each student solve it a little bit differently. Some were better than other. But yeah, I will share the solution with you in a couple of weeks. So once I close out the extra credit stuff, I will post that so you can see. I see some chat questions. Okay. A lot of us are, I'm that person. Okay. That's okay. What we'll do is, you know, I've had students that turn in, like, they were pretty clever about handling the individual input, because you can only get one character at a time, until you start practicing on how to move stuff around with LC3. Then you can say, oh, you know, because as soon as it reads it. So just like how you wanted to do put, you can do in, and then convert it every single time and move it. So you would have to loop it. Think about that, right? Like if I have one input and then I wanted to convert it, and it's the same task over and over again. So you have to ASCII convert every single character, as in you wanted to represent a string. So you just wanted to send it into a loop, and that's more of an efficient solution. So that's a hint for you. But other people, what they did was they just move it across different register, and that's okay too. But you have to track your register and then end it up with, you know, a bunch of register to work with. So yes, so I will share with you some solutions that, you know, students had posted, that has submitted, so that way you can see how that is solved. Okay. All right. Any other questions? So I hope you enjoyed the day of the week lab. That's actually a lab that they do at the university. So if you come across that again, then you would know how to solve it. And then we would do Fibonacci this week. So we would use loops, we would use branch, we would use subtraction, etc. Okay, so check out your lab before we do it if you have time. Okay, type your name into the chat. If you have any questions, let me know. And thank you for attending. I'll see you on Thursday. Yay.
All right. See you Thursday.
Bye.
See ya.
Bye. Take care. Have a good night. You're welcome. Good night.
Professor,
Yes.
I have a question. Sorry, I closed it. Let me see. Because it's just like the one, I think it was the one where they had the answer that was logical error. Like
Okay.
how is that a problem? Because isn't it gonna give you a positive like all the time? Oh, is that what the problem is?
Yeah, so if you get a negative, so like if your code gets a negative, but the problem asks for this, right? Then somewhere is wrong. And that happens too, because when you do like in the LC3, if you branch, or if you subtract it a certain way, because when you branch, remember you have to subtract, right? Like if I do x plus y, and then I got a branch for positive, right? But in order to branch, I have to do a subtraction. Okay. And if I subtract the wrong value, then I might get a negative, and that would become a logical error.
But even though it's still inside the absolute value?
It doesn't matter, because in absolute value in LC3 it's just branching positive. There's no absolute value in the code, right? So how do you code this? You code it by doing what? X plus y, but how do you check for this part? This part right here is greater than 0. You have to do subtraction, right? So if you branch, so if you say, okay, x plus y, so let's say that if I have x is 1 and y is -1, right? Having to put that here, that won't be true in that case, because if I have x plus 1 and y is -1, force it to be positive value, then it is greater than 0. So in that case, if I hard coded it wrong, I can get a logical error.
Oh, I see.
You see what I mean?
Yeah.
So if I have the wrong input, that causes the data error, but it also causes me to have a logical error. Because if I hard code in y as -1, 1 plus minus a 1 is 0. It's not greater than 0. So I will get a logical error.
Oh,
You see
okay.
what I mean? Because
Yeah.
in LC3, we have no absolute value. We can only check by subtraction or adding of the 2 complement, but to check the greater than, we have to branch it for positive, negative, or 0. So if my condition is untrue, that means that I'm logically wrong. You
Right.
see?
Yeah.
Yeah. So it really depends on the programmer, because in the case of other languages, it's a lot easier to handle this statement. But in LC3, you have to manually use arithmetic, and if you have the wrong data, you're gonna have the wrong output. If you have the wrong logic, then you're gonna have the wrong output.
Okay.
Yeah.
I see. Thank you.
You're welcome. Other questions? Okay, good night.